Hello everyone. Next topic that we are going to discuss is the Brownian motion. Okay. So, before we actually define, one can straight away start with defining and then looking at its properties, because that is what we need as we go ahead for using in stochastic calculus as well as a modeling for financial asset prices. So, let us see how this Brownian, why this particular thing Brownian motion came into picture, right. So, this the intuition behind is what we will try to give, and so that is also, I mean, from another angle if you look at it, it also show that such a stochastic process exists. Okay. Now, to give this intuition, let us consider and go back to our binomial asset pricing model, where what we did. Okay, so, we considered a binomial asset pricing model wherein the risky asset follows a sort of a binomial tree as time progresses, right. So, that is what we keep in mind, you recall, and we will now see that if you scale that binomial model in a particular way, then you are going to end up with a model in which involves the Brownian motion. So, and hence we can we will be able to relate this binomial model to the geometric Brownian motion model, which we are going to use it as the model for the asset prices in continuous time finance, right. So, let us see how this comes. Okay. Now, the case that we consider is basically r equal to 0, but r greater than 0 can also be done in a similar way. For simplicity, we just take the case r is equal to 0, and what we do, you pick an interval say 0 to t, okay, and choose an integer and construct a binomial model for stock prices, right, that takes n steps per unit time. Okay. So, recall binomial model, we said time 0, time 1, time 2. So, now what we are going to do is that between 0 and 1 we are going to have n time points, and each of these would now become the new time points, if as if if you look at the original binomial model. Okay. And we going to increase this number of steps in to the limit, so that we are looking at the stock prices at every time point along the time axis rather than at 0, 1 and so on. So, how do we make this continuous time analog? Is that you divide, instead of looking at 0 and 1, you look at 0, half and 1, 0 and 0.1, 0.2, 0.3, 0.4 and 1, and then you keep on increasing number of points, then you get to the limit in the continuous time, right. So, that is the way we approach any modeling from discrete to continuous when we make a movement, right. So, that is precisely what we will do. So, now what we could consider an up factor for which we may make it as dependent on n, right, as 1 plus sigma by root 10 and a down factor of 1 minus sigma by root 10 for some sigma positive, and r we have already assumed to be 0. So, this satisfies the no arbitrage condition for the binomial model, right. Now, once we are given this, then the risk neutral probabilities, which we know, minus dn by un minus dn, will work out to be sigma over root 10 by twice sigma over root 10, which is equal to half. So, that implies my q tilde is also equal to half. So, this is what you have. Okay. Now, recall the asset price in a binomial model, the asset price at time n is determined in terms of the initial stock price S naught and the number of up movements and number of down movements in the stocks, right. That essentially means the result of first n or n tosses in if it is n period model. Now, okay, so this n and t, okay, we also have this additional condition that we pick nt to be an integer. Okay, so if not, anyway there is nothing is going to be lost, but this is for convenience that we picked in this way. So, we will take for easy understanding that it nt to be an integer. So, we pick n and t such that this is true. Okay. Now, let us define few quantities. So, let us call, so basically if you are looking at t time units 0 to t and each time unit has n time points, then total number of time units or number of tosses that you would associate with such a binomial model would be nt number of tosses. So, out of those nt number of tosses, this is h underscore nt defines the number of heads in nt tosses, right, nt number of tosses, and equivalently t and t will be the number of tails. So, what you have h n t plus t n t, if I add these two, this would sum to n t, right. This is what then you would end up with this, right. So, you are also let some m n t to be the differences h n t minus t n t. Okay. One can also identify the m n t to be a symmetric random walk process. Okay. This is observation which if you associate an up movement to each up movement of unit size 1 for each of these heads and tails for -1, then m n t to be, you can observe that this is essentially mn or mnt in general is you can associate a symmetric random walk. People who do not know what this is simple, another simple stochastic process, but we do not need that as such, but we just need this to be some quantity this. Then I can see by solving these two equations, I can write my h n t, I can write in terms of n t plus m n t and t n t to be half n t minus m n t. Okay. Now, if I look at the stock price, which we write in general S n t to be S at 0 and u n to the power h n t d n to the power t n t, right. So, this is initial price multiplied by the u n to the power number of heads and or up movements and d n the number of down movements multiplied. So, this is what would be the stock price. Now, u n v n I know, h n t n we know. So, we can express this as S naught times 1 plus sigma over root 10 to the power half n t plus m n t and 1 minus sigma over root 10 to the power half n t minus m n t. Now, the question is, like when if you want to look at the limiting cases of this stock price process as n tends to infinity, we are looking at what is this quantity is going to be as n tends to infinity, right. So, that is what is the case here. Now, for this to look at what is S n t as n tends to infinity is what the question. Now, to get the answer, So, we need a result from probability theory, which we already said about the name central limit theorem, and CLT for this case with appropriately defined M and T that is the following. You fix a T now as n tends to infinity, the distribution of 1 over root 10 m and t. So, remember this we are looking at as if we are assigning an addition to this process of 1 for every up movement and minus 1 for every down movement, and then you are now scaling it to this. That is what you are looking at it, right. So, this is called the scaled symmetric random walk in this particular case, right. So, the distribution of this, which is a scaled symmetric random walk, converges to the normal distribution or Gaussian distribution, whichever we want, with mean 0 and variance t. So, this is what is the central limit theorem specialized to this particular sequence of random variables that we have here, okay, m and t. So, I mean, or you take it that this is what is happening for appropriately defined m and t, whichever way you look at it. So, this is the result that we have. Now, if we use this result, then we have the result for our question that what happened to this S and T as n tends to infinity is the following. Now, as n tends to infinity, right. So, the distribution of S and T as given above converges to the distribution of S of t, which is S0 into e to the power sigma of some W t minus half times sigma square t, where this W t is it's a normal random variable with mean 0 and variance t. Okay. So, this is what we can show, okay. And so, this is what is called as that means that ST is what we say is log normally distributed, right. So, in the limit what we get is that the distribution, this is a distributional limit, distribution of this converges to the distribution of this ST. Now, this ST is given by this expression, which is in terms of this W, where W is normal. So, anything of this form is what is called the log normal. If you want to see generally, so any random variable of the form some c to the power e to the power x, okay, where c a constant and x a normal random variable, okay, is log normal, which means this y in this form. So, if I take my log of y, that will be will be given x, right. So, x is normal. So, log of y is normal and hence y is log normal. That is how we look at here. So, in this particular case the quantity in the exponent, it is sigma to the power w of t minus half sigma square t. This is normal distribution with mean this and variance as sigma square t. So, we will use this notation to denote some random variables which is distributed as normal. The first quantity would be mean, the second quantity would be the variance of the normal random variable. Now, while going forward, so we will need some properties because now this normal thing has come. Okay, this Wt is the normal and Wt is what is going to be the Brownian motion component that we have, and this is what we call it as the exp e to the power something. This is what is called this as a geometric Brownian motion. So, St is given by a geometric Brownian motion is what our continuous time model would be, right. Now, while working with that, so we need again some note. So, what we call this MGF of a normal random variable, which convenient in many places in our calculation that we will use. So, let us give it as an expression. If x follows normal mu sigma square, then the MGF of x, which is we call it as mxt, this is given by mxt which is equal to expectation of e to the power tx, right. This is one of the important expectations formulas that we might use, and plus half sigma square t square for all t in R is what, and MGF may not exist as we know, and in this particular case MGF will exist for all t. So, this is what it is. You know what is the meaning of MGF, that it is if I express as a power series in terms of t square, the coefficient from the coefficients I can obtain the moments of this particular random variable. So, this expression for any random variable x with normal mu sigma square, the expectation of e to the power tx r is equal to this expression. This expression we may use it multiple times in many situations. So, let us give it as this. Okay. So, now you see this Wt that we are getting as the limit of this S and t is what is basically going to be our Brownian motion, right. So, its properties also again from this symmetric random walk case, like properties also it inherits, and those properties define a Brownian motion. So, now let us precisely define what we call a Brownian motion, or another name is a Wiener process. Okay. Though it is Robert Brown who observed this process and discovered, as stated by Einstein, it was Wiener who gave who derived the mathematical properties. So, it is also equivalently called as Wiener process or Brownian motion. Both would mean as far as we are concerned one and the same. Now, what is this process? Okay. So, let us precisely define. So, like any random process that you have, so you have an underlying probability space on which the random variables are defined. Now, a stochastic process which we call Wt here with values in R, which means the state space is R, is a Brownian motion. Shortly we may call it as in short by Bm, if it satisfies these 4 conditions that we are going to list. A, W at 0 is 0 Almoshuli sense, even if you do not write Almoshuli sense, it will be still fine. If you understand what this means, it is also that with probability 1 this is true. Now, these sample paths, which is as a function of t, if I look at this process, are continuous almost surely again. Now, see for any time points that you pick here, the increments, right. So, these are the following are is what we call the increments of the process over the subinterval, which means the the state change process in the subinterval points is what then we call the increments. Now, that is essentially this, the displacement of the process from the from T naught to T1 is what this, and this quantity is what called increment to minus W T1 and so on, the last one being W Tm minus W Tm minus 1. What are these? So, these are independent, right. So, we know when we say some n random variables are independent, it is precisely that quantity. Now, D, the last property, for any 0 less than or equal to s less than t, the increment, which is Wt minus Ws, is what is increment, right. The increment has a normal distribution with mean 0 and variance t minus s, which is nothing but the given by the length of the interval. So, this essentially means that the if I take increments in this process, the increments would also be what we call stationary increments, right. In only it depends on the length of the interval, not on where you place this interval s to t. So, this is what. So, this is essentially normal 0 t minus s random variable. So, these 4 properties is what defines a Brownian motion. It should start at 0, the process is starting at 0 in the beginning at time 0. The sample paths, which means for each of these omega, if you fix an omega, you are going to get a path of a realization of the stochastic process, and that paths are continuous, and the increments are independent and stationary, and also the increments are normally distributed with mean 0 and variance given by the length of the interval. This is what defines the Brownian motion in this particular case, right. Now, if I look at since we talked about sample paths, right. So, if I look at a typical sample path, so where in the x axis I have t and in the y axis I have W t, sorry, I have not yet used this thing. So, I will just so it is W of t, it should start at 0. So, it will start at 0 here, right. So, let me start with red itself. It starts at 0 and it will at each time point it may go up or down. So, but typical process, if I look at it will have this kind of these kind of behaviors is what then you would observe. Okay. So, this oscillations that it can be little bit more into this form also, right. So, this is how it will look like into this typical sample path. Okay. So, this is what we call the sample path. This means as time goes, what is the realization? Before time t, it is random, but once it comes to time t, then what is the value of the process, and hence you have this realization or the sample paths that you have here. Now, this definition also gives us the various quantities that you can compute with respect to this Brownian motion. If you are interested in those, say for example, if I look at W at 0.05, if you want to look at its distribution, you can see that it is 0.25 is the variance. Suppose if I look at W7 minus W3, I know that this is distributed as normal 0 and with variance 4. Okay. So, this is what and any calculation with respect to this W, since you know it is normal distributor, so it boils down to the calculations connected with the normal distribution as far as the distributions, properties, probabilities with respect to Brownian motion is concerned. If you want to know what is the probability that at time 2, say for example, this quantity, right. Suppose if I want to see W5 is greater than 5, suppose how do I compute? Because I know its distribution, so I can compute these probabilities and so on. So, all these calculations you can do with respect to by using the normal properties that you have here. Okay. Now, for our convenience and ease of use little later, so we can also have an equivalent way of defining or equivalent in terms of characterization. It is not equivalent characterization really, it is characterization. So, it is also equivalent to that definition, characterization. Okay. And in this part A and B remains true. So, A and B remains. Now, the C and D could be replaced by the following. Okay. Now, because the increments are say W T1 minus W T naught and so on, W T m minus W T m minus 1 are independent and normal. This implies that this quantity, the random variables which are W T1, W T2 and so on, W Tm. Now, these are independent and normal. Now, you can see W T1 is same as this, W T2 if I have to add, I can express this in terms of the first two in those previous line that we have written as the increments, right. So, you can express as a linear combination of these independent normal. So, this will be, these are then jointly normally distributed. These are jointly normally distributed, and this vector W, which is essentially W T1 and so on, W Tm will has 0 vector, because each of this random variable has 0 mean as its mean vector. Now, we only need to know the variance covariance matrix, for which we just compute, for which to get that we just compute, you pick a S which is less than T and look at covariance of these two quantities W at S and W at T, which is because mean is 0, it boils down to this quantity, because this is what is now the covariance is, because means are 0. Now, this you can write it as, so these are not independent and so on, right. So, you cannot, you really have to evaluate, but in a convenient way you can write this as Ws and Wt minus Ws plus W square S, right. So, what I do, add and subtract Ws to this Wt and then leave this. Now, since expectation operation is linear, I can separate this, and the first quantity, if I look at it, these two, right. So, these and these are independent. So, this means that I can write this quantity as expectation of Ws into expectation of Wt minus expectation of Ws plus expectation of Ws square is again, because expectation of Ws is 0, this is nothing but the variance of this. So, which is essentially variance of Ws, and these quantities are 0. So, this quantity is S. So, this is S. So, if I pick a S and T where such that S is less than T, then the covariance between Ws and Wt is S, which means the minimum. If for arbitrary S and T, this covariance of Ws and Wt is minimum of S and T, right. So, if I use that, now my variance covariance matrix which is we call C as per our earlier. So, this is nothing but, sorry, this is also T1, T1 and so on T1, this is T1 and this is T2, this is T2 and so on, this is T2, this is T1, this is T2, this is T3 and so on, this is T3 and so on, T1, T2, T3 and so on, Tm. So, this particular structure, right. So, which means that what is the equivalent characterization now? Without writing, A and B remain, which means process starting at 0, process has continuous paths we have. Instead of saying that the increments are independent and the stationary and it has now distributed, you can say that these particular random variables, these set of random variables are this vector W has a 0 mean vector and variance covariance matrix as given by this C, then that process is a Brownian motion process. This is the equivalent characterization which we might use in some places. Okay. Of course, we may have some more equivalent characterization which will come little later depending upon the other property, but this interchangeably one can use. If you want to prove some process is a Brownian motion, either you can use the basic definition or this equivalent characterization. Okay. In the same way, any other equivalent characterization, if it is there, that can also be used to prove that this process is a Brownian motion. Now, connected with this Brownian motion as we go along, we will also need another concept which is called a filtration for Brownian motion. So, this is slightly different from the general filtration that we talk about. Okay. So, you will in a moment you will see what this is. What is this? So, you have a W of t which is a Brownian motion, be a Brownian motion which is defined on some probability space. Okay. Now, a filtration for Brownian motion is a collection of sigma fields, say f of t for t greater than or equal to 0, and that satisfies three properties. A, the first one is called information accumulation, right. The usual the first condition that you require here, which is for 0 less than or equal to s less than t, every set in Fs is also in Ft, which is f of s is contained in f of t, right, which means that at time s and at time t, if you look at this as information, then the time t information is at least as much as what you had at the information at time s. Nothing is lost from when you move from s to t, information only accumulates. The second is adaptivity. The second is adaptivity, which means that what? For each t, Wt is, sorry, I have not yet measurable, which means the information in Ft is such that we can determine what is the value of the process at time t, right. So, that is what Wt is, Ft measurable. Oh, sorry, this is also should be this notation. C, independence of future increment property. Okay. That means what? You pick a t and a u such that it is greater than t, then the increment, which is w of u minus w of t, is independent of w of t, sorry, independent of f of t, means the information in the filtration and information especially at time t, the sigma field which is f of t should give no clue about any future value of the process w, which is the Brownian motion. So, which means this increment should be independent of this Ft. So, in the normal in general filtration, only part A you might call simply as filtration, but whenever we say a filtration for Brownian motion means that it is connected with the Brownian motion in some way or other, then that means these three properties should be satisfied. That is what you call a Brownian motion, a filtration for a Brownian motion. Now, if I pick any random process delta t, and if I say that that process is adapted to this filtration, right, which means that that process is measurable with respect to Ft. So, that is also true with whatever you have it here. Now, how do we construct the filtration, such a filtration? There are two possibilities, okay, which normally happens. Okay. One is you take this at time or this filtration to be the filtration generated by the process itself, where what we mean when we say Ft of W, right. Recall F of T is the sigma field generated by some Ws this collection, right. This is what we have. So, this means that the filtration has exactly the same information as that of the one that you might have by observing the Brownian motion up to time t. The filtration is, in this case we say that the filtration is generated by the Brownian motion. Okay. So, this Fw is nothing but the filtration generated by the Brownian motion is what then you have it here. Or the second case could be you could have a general filtration with these properties, something like the filtration could be not just W, some x, y and so on, so many processes also might be there to generate this. But this should satisfy the condition that we have, which means that this filtration, when we take this as a filtration for W, the additional quantities that you have here, that this x, y and these things again should give no clue about the future behavior of this W, then only this will become a filtration. So, this filtration could be simply generated by W or more than one or more of the processes apart from W also can generate such a process. But what we have to keep that in mind, if the additional process that you are using while having this Brownian motion for the filtration for this Brownian motion, again should not give a clue about the future behavior of this W. That is what one needs to keep in mind in this case. Okay. Now, once we have these definitions, then we look at certain properties of this Brownian motion, and especially there are two properties or rather three properties of this Brownian motion which are important. One is the Martingale property, the other is the path properties which lands us in the quadratic variation property, the third is the Markov property. Now, let us take first case as the Martingale property or Martingales connected with this. The result is that the Brownian motion is a Martingale. Okay. So, the Brownian motion means like what we have used so far is what this part is essentially, right. Now, what you have to prove. So, you have to prove for if you pick these quantities be given, then the Martingale property, then you have expectation of W of t given f of s, right. Again you see when you look at this, W of t is neither measurable with respect to f s nor independent of f s. So, really you have to evaluate this. So, what you can do, you can add and subtract something, some manipulations you can do, so that you can use the properties of conditional expectation to simplify this process, right. So, what we do is you add and subtract and add given f of s. Now, right. So, this quantity you can see is independent. First of all, you can use the linearity property to express this as a two conditional expectation, sum of two conditional expectation. The second property that you would use is that this Wt minus Ws is rather independent of Fs and Ws is Fs measurable. So, you will use all those properties to end up with, right, simply since this is independent of that. So, this is simply Wt minus Ws plus this is measurable. So, this is Ws and this quantity is 0. So, you end up with Ws. So, this is true for arbitrary s and t, right. So, what is the property that we have shown? This is the Brownian motion. Sorry, Brownian motion is a Martingale property. Of course, Martingale's other properties are there, which are the things to expect and this thing. So, you have this filtration and everything you have, right. So, the other conditions are automatically satisfied, only the conditional expectation property we need to verify, and which we have verified and which we have seen that this is true. So, Brownian motion is a Martingale. So, what we have here. Okay. By the way, before we go further, there are notes. So, the Brownian motion that we consider is sometimes also called as sometimes inconveniently standard Brownian motion. Okay. So, that is what we mean whenever we say simply Brownian motion without any adjective. Of course, this essentially mean connected with the standard normal in some sense 0 1. Instead of that, if I put some other, then I am going to get a shifted and scaled Brownian motion. or with drift or in other cases that you see. So, that you will whenever we will call that specifically. The other thing is the standard Brownian motion. The other thing is notation wise, again we will use for the for this lecture purpose alone. So, Wt will be denoted by W I use subscript T for ease. There is nothing else other than this, but it is actually it should mean this means that this. So, that you remember, and so that little neat when we are writing this. That is the only reason we are doing this, other than that there is nothing. Now, the simple Brownian motion, a simple standard Brownian motion is a martingale that we have shown, right. Now, there are two other martingales connected with this, which is are of importance to us. Okay. Another one, so this is martingale 2 is what? Wt squared minus t. This process is a martingale. Okay. Now, hint for proving this is you write this Wt square as Wt minus Ws square plus this is 2 times Wt minus Ws into Ws plus Ws square, and you know what we have done here, add and subtract Ws and then appropriately keep this. Now, if you apply your this property, then you will be able to show that immediately this is a martingale. The other martingale, which is martingale 3, which is also known as exponential martingale. A form of this is already you have seen earlier, right. This is one martingale. The other martingale, which is exponential martingale, is basically if I pick a constant sigma, for sigma a constant, if I look at this process e to the power sigma of Wt minus half sigma square t, if I look at this, this is a martingale. Okay. Again, you can hint for proving is 2 steps. One is this sigma Wt minus half sigma square t. Again, you can write it as sigma of Wt minus Ws plus sigma Ws minus half sigma square t as another term. Now, you see this whenever you want to show this martingale property, this will be independent of Fs, this is Fs measurable, you can pick it up, and then this will become simple expectation of sigma e to the power sigma of this, which again you can use the MGF of a normal 0 t minus s random variable, right. We have already seen, if you use that expression, then you will be able to show that this is a martingale 2. So, this exponential martingale also will play a crucial role in the analysis when we go forward. Okay. So, this is what is the first group of property which we call as the martingale properties, and now we will go to the second group of properties which we will call the sample paths. We look at the sample paths. For any stochastic process, the sample paths means a realization, right, what you have actually observed. Okay. Now, for this let us look at the properties for which we start with a simple definition which we call the variation or the first order variation. Simply, sometimes it is called simply variation, but in this particular case we really mean the first order variation of a function, say f, which is we are defining in is defined to be, we call this as some first order variation of the function in 0 to t of the function f as limit tend to 0 of j is equal to some n minus 1 f t j plus 1 minus f t j, where this pi means this partition of this interval and this. Okay. Actually speaking, like instead of this limit num of pi tends to 0, one should say that the lim sup, but anyway for the sum should be the exact thing. So, which we can still take lim here and then we can describe it rather than making it a little easier, that is it. Okay. Now, this is what we define to be the variation. Now, if you imagine what this tells is that if you look at here, you have an interval 0 to t, you are partitioning this interval into some n points or n sub intervals, and in each of these sub interval you are actually looking at the absolute value of the change in the function value, right, which means how much the function has moved, right. So, you are making the absolute value, not up movement alone or down movement alone, or you are neither subtracting, you are just taking the adding the changes that happens in the function. Now, as you increase the number of partitions, where the norm of partition means that the maximum length of this any of this sub interval tending to 0, right. This norm of pi means exactly that, as we have seen earlier. So, as you increase the number of points more and more, so it is really is going to be the, you are going to evaluate the function, looking at the function and its how much this has made the movements, the amount of movements that you have, amount of variations of f during 0 to t is what is this variation function will give. Now, you can note easily that if the function is such that the derivative exists, okay, then by MVT, which you would have observed in ordinary calculus theory, that is mean value theorem, right. By using the mean value theorem, you can see that this particular variation can also be j 0 to n minus 1. This could be written as some f dash of T j star times T j plus 1 minus T j, where T j star is a point in the sub interval T j to T j plus 1, right. This essentially in the limit, this will be equal to, because this exists, so this will be equal to f dash of t dt is what then you will get. So, where this belonging to Tj to Tj plus 1, right. This is what you would see. So, essentially the first order variation is nothing but this quantity is what then you can observe. Okay. Now, there is another, this is the first order variation, and similar to that you can also define the what we call quadratic variation. Okay, let me go to the next page itself. What we call quadratic variation, as opposed to the first order variation, we will also deal with everything remain the same, the function and the partition and everything. Only thing is the quantity that we define is this one. Whatever condition that we stated earlier for first order condition, that remain the same, and then but this quantity now will be given by f of Tj square, right. First order variation, we looked at the absolute value of this function and the difference in the function at the subsequent points in the partition. Now we are looking at the square differences, right. This is what is a quadratic variation, and it can be shown easily that if f has continuous derivative, which means in the first case for f dash exists we assume. Now if f dash is also in addition is continuous, then one can show that this quantity is 0, okay. And this is for functions that we encounter in the ordinary calculus. Most of the time it so happens that the function has continuous derivative and the second order variation is or quadratic variation. This is second order variation, as the quadratic variation is 0, and hence we really don't bother too much about this quantity in the simple ordinary calculus. But of course, there also you would at some times want to look at that. But in stochastic calculus, this plays a major role precisely because what we are going to see next is a property, okay. And that is because of that okay, this quadratic variation is important in the case of stochastic calculus, because the function that we have now taken up is the Brownian motion, and the Brownian motion's one important property is the nowhere differentiability property of Brownian motion, which we take without any proof because the proof is involved. What we say is the with probability 1, the Brownian motion, which is Wt, is non-differentiable at any t greater than or equal to 0. So, what this means is that if I take a path of the Brownian motion, you can go back and see the sample path that we had just this up and down movements, very sharp movements that we have. So, all those sharp points, as you know, like for example mod x at 0 is non differentiable, right. So, because it has a sharp edge. In similar way, these are all have a sharp edge paths. Path is full of sharp edges, which means at no point of time you will be able to differentiate. That is what it means, which means that for a Brownian path, okay, say W of t, there is no value of t. We are saying all in the almost surely sense. So, for which this is defined, okay. So, this is done. So, which means the first order variation, second order variation that we have noticed that f dash exists here for Wt case that does not exist, okay, and there is no question of continuous everywhere property also. So, these whole things will break in the ordinary calculus thing, and this will break in the stochastic, which was there in the ordinary calculus will break in the main property is this nowhere differentiability of the Brownian motion paths, which we are taking it granted because the proof requires lot of effort, and of course, those who are interested you can always look it up any book, it is not a major issue at all, right. Now, what is the main result that we have? Before we look at the first order property, we look at the quadratic variation property, that is what is the major property of this Brownian motion paths as a sample path property. Now, let W as usual, this is what it is, be a Brownian motion, then t for all t non-negative almost surely. So, the sense that we talk here is almost surely, but in a moment you will see like we are actually not proving this, but we are proving something slightly different, but this can also be proved using advanced results in the stochastic calculus. Okay. Now, so basically what we want to show is the quadratic variation process, the quadratic variation of this is equal to t. Now, let us take a partition T naught, T1 and so on, Tn be a partition of the interval 0 to t, and we also define the sampled with respect to this partition, the sampled quadratic variation for this. Now, what we want to show? To show q pi tends to t, right, almost surely, right, that is what we want to show, right. Now, how do we show? So, this is basically as tends to 0, this is in the almost surely sense we want to show, and this is as tends to 0. Now, what we will show? We will show is expectation of q pi is t and variance of q pi is tends to 0 as norm of this tends to 0, which is actually L2 convergence, but technicality apart, it can also be shown that this is true. So, whenever this convergence takes place, there is a subsequent along which the convergence almost surely, and hence it can infer from that. So, we will not worry about that, we will just show this, we will say this. Okay. Essentially what we are proving is L2 convergence. So, this is L2 convergence, this is for only for more technically or people oriented, otherwise you do not worry about it. Okay. So, you say that it is accumulated in this manner. Now, first we will show what is expectation of q pi. Expectation of q pi is, q pi is given to be this, right. Q pi is what basically this quantity is. So, this is inside summation, if you look at it, it is what? So, if I take expectation of that, that means the variance of this. So, that means this is 0 to n minus 1, the variance of each of these quantities, and they are all independent. So, expectation of this q is simply this, okay, expectation of this one only, which are not variance that we are looking about. So, this is expectation of this, which is variance of the increment, which is Tj plus 1 minus Tj, because given by the length of the interval, and if you sum you will get T quickly. So, there is nothing great or nothing complex to show that this part is true. But for the other part, which is the variance part, first we will look at the one quantity inside the sum, which is essentially variance of Wtj plus 1 minus Wtj square. This is what we look at it. Okay. So, this is means expectation of Wtj plus 1 minus Wtj whole square minus its mean and the square is what this quantity is. Now, you can again expand and write this as expectation of Wtj plus 1 minus Wtj to the power 4 minus twice Tj plus 1 minus Tj, expectation of Wtj plus 1 minus Wtj to the square plus Tj plus 1 minus Tj the square. Now, here we are using an important property for normal x follows normal 0 sigma square. Your expectation of x to the power 4 is 3 times sigma to the power 4. This is one of the properties of normal random variable. if we use that, then you get this as 3 times Tj plus 1 minus Tj square minus this is again 2 times, this is one more t minus a, this is plus. So, again I would say that this two quantities simplified will give you this, which ultimately resulted in 2 Tj plus 1 minus 2 Tj. Now, if I look at variance of q pi, as summation j is equal to n to n minus 1, variance of the quantity here, because each one of them is independent, there is nothing more that is resulting here. So, this is essentially summation over j twice Tj plus 1, sorry, this is a square here, Tj square. Now, this is less than or equal to, instead of one of this Tj minus 1 minus Tj, I replace by norm pi, the remaining I leave it as it is. So, then it will end up with summation twice norm pi times Tj plus 1 minus Tj, which is again equal to 2 times T and norm pi, which tends to 0 as norm pi tends to 0. So, and hence we have shown that the quadratic variation of this is true, is what is given by this. So, this is the proof, right. We have shown it in almost L2 convergence, but actually this is true in almost every sense. Okay. Now, we write this, that is what is important, we write this informally in the following form: dw of t is equal to dt, which is actually equal to 1 times dt, is what then you would see that this is what you will use. So, this is what is the form that you will write, okay, as dwt, which essentially means Brownian motion accumulates quadratic variation of at the rate 1 per unit of time, that is what it means, right. Now, this quadratic variation is what is will turn out to be the source of volatility in the asset prices driven by the Brownian motion based models. Okay. So, that is what will come out to be the case that we are here. Okay. Now, in the along similar lines, you can also show two other quantities. So, this is quadratic variation of W with W, which what we call the further results or remarks along similar lines, similar processes by using. You can also show this quantity of WTj plus 1 minus WTj, Tj plus 1 minus WTj equal to 0, which we write informally again, in this form dWt dt equal to 0, and one more limit to 0 summation Tj plus 1 minus Tj square, which will also turn out to be equal to 0, which we write informally as this. Okay. So, these are the three basic results, basic formulas that we will again you can show it in along similar lines that we have seen. I mean, this is much easier here because one of them is normal function and only W is we are encountering here. So, we can show simply using the simple properties these two. So, these are the three bread and butter formulas that is going to be for all the pen and paper calculation that we are going to use in the stochastic calculus quantities that we have. Okay. Now, by using this, one can also show, by using the quadratic variation property of this W, the first order variation of this Brownian motion is infinite in the almost surely sense. Okay. The hint for that is essentially you look at this WTJ plus 1 minus WTJ square is less than or equal to some maximum of W T some k plus 1 minus W T k into summation of W Tj plus 1 minus W Tj, right. So, this is what, so this is k less than or equal to n. So, this is what, right. So, you will have this is n minus 1, right. So, this is what you have. So, this is the hint, you can show that this is the case. Similarly, the higher order variation, the cubic variation or any other higher order variation is 0 for the Brownian motion. First order variation is infinite and hence only like we are ending up with this quadratic variation being positive, and quadratic variation is positive and for finite interval it is also finite, and the cubic variation or any third, fourth and higher order variations, they are all 0. So, these properties we will use later. So, we will just mean in this particular case. So, what did this mean? As you say is this summation of W Tj plus 1 minus W Tj, sorry, this is absolute value, this is absolute value to the power 3 is 0. That is what we mean when we say cubic variation is 0. Okay. So, this also leaves us with a result cubic once we have this quadratic variation property called as Levy's characterization of the Brownian motion. So, what is that? So, you take a Martingale or Levy's Martingale characterization, be a Martingale relative to a filtration f t. Now, you assume this process is also starts at 0 and m t has continuous paths, okay, and this is equal to t for all t, then mt is a Brownian motion. Okay. Again you see m0 equal to 0, mt as continuous path is there here also. The second and third and fourth properties is replaced by being Martingale and the quadratic variation property that we have it here in this case. Okay. So, this is what we have with respect to the second group of property. One final group of property that we would see is this Markov property, right, which we say is, what we say is the following. Let as usual W2 be a Brownian motion and Ft be a filtration for the Brownian motion. It need not be generated by Brownian motion itself, it could be any filtration for the Brownian motion. Then Wt is a Markov process. You can quickly see how this is true, and then to show what we have to show. So, proof to show what we have to show is the following. Whenever your 0 less than or equal to s less than or equal to t, and f a Borel measurable function, right. There is another Borel measurable function g such that expectation of f of w t given fs should be g of ws. So, to show that w is Markov, we need to show only this part. Okay. Now, write this left side quantity expectation of f of w t given fs. Now, you see w t and fs, if you see the connection, it is neither measurable with respect to fs nor independent of fs, but you can write this as expectation of f of wt minus ws plus ws given fs. Now, if I call this quantity as one random variable, this quantity as another random variable, and you would see the first one is independent of fs, the second one is measurable with respect to fs, then I can use, now you can apply your independence lemma, right. Many a time that is what we use to show that some process is Markov, also to compute the condition expectation. In both cases, that is what is being used. So, in this case you can simply use, so what is the relevant g of x function? The g of x function is now f expectation of f of w t minus w s plus some x dummy is what then your quantity here, which is again you can see that it is 2 pi t minus s, and this is minus infinity to 2 f of some w plus x e to the power minus w times 2 times t minus s t w. This is the g of x function, right, and this quantity is now g of w s, right. So, it is a function of s, and where g of x by independence lemma application, you can show that g of x quantity is this. Once you evaluate this, you get the g of x, replace x by ws, then you get the quantity here, and this is depends only on ws, and hence this is Markov, right. So, we can show that easily this is Markov. So, basically what it means that if you have to evaluate a function of Brownian motion at time t given a filtration for the Brownian motion, then what you need to remember is only ws and its progress from s to t is what you would require to evaluate this. Okay. So, that is what your rule implication. So, these are the properties of Brownian motion that we will need, we will use in our further when we go ahead with stochastic calculus. We will see in the next lecture about the stochastic calculus.